Yes, so we are in homomorphism and isomorphism. In last lecture we had discussed isomorphism, and we have also list some groups from number theory, that groups are isomorphic or not isomorphic. And we have also seen some results that every finite cyclic group is isomorphic to Zn if the order of cyclic group is n, and any infinite cyclic group is isomorphic to Z plus. And if you have if every group is isomorphic to itself, if G1 is isomorphic to G2, then G2 is isomorphic to G1, G1 is isomorphic to G2, G2 is isomorphic to G3, then G1 is isomorphic to G3. That is if you collect all the set, if you have a set of groups, and if you define a relation on that set that two groups are related if and only if they are isomorphic, then this relation is an equivalence relation, right? Okay, so now let us prove one important result in number theory known as Calais theorem. So Calais theorem. So what this result says, every group is isomorphic to a group of permutation. Every group is isomorphic to a group of permutation. So first of all, let us just recall what is a permutation. We have studied this Sn group of permutation, right? But in broad sense, what is a permutation? So already we have defined in previous lecture. Let X be a non-empty set. Let X be a non-empty set. Then you consider AX. AX is what? It is a set F. It is a set of functions F such that F is what? F is a mapping from X to X such that F is 1 1 and onto. Then this set AX with the composition of function forms a group, and this group is called group of permutation. And if X is finite and if it contains n elements, then we denote if X is cardinality of X is n, then this we use another notation for AX, and that is what? It is Sn. And we have also studied this Sn in detail as a special case of AX, right? So we know that this AX is what? It is a group of permutation. तो ये result क्या कह रहा है कि you take any group, then you will find some X so that it will be the isomorphic to AX, or you may say it is a isomorphic to some subgroup of AX. वो सबग्रुप, वो जो सबग्रुप है वो अपने आप में एक ग्रुप है. तो AX का कोई भी सबग्रुप लूंगा मैं, शायद फॉर एग्जांपल से H इज अ सबसेट ऑफ AX, इनफैक्ट H इज अ सबग्रुप ऑफ AX. तो H में भी क्या आएंगे? परम्यूटेशन ही आएंगे ना. H will contains permutations, and if I saw that G is any group and G is isomorphic to H, where H is a subgroup of AX, then we are done, right? So let us try to prove this result. So any group or every group is isomorphic to a group of permutation. So how we prove it? So proof, let G be any group. Let G be any group. For A belongs to G, for, let me write in this way, for every A belongs to G, you define TA. TA is a mapping from G to G, and it is defined as TA at X is equal to AX for all X in G. So G is a group. You take any element from G and corresponding to that element A, you define this map TA suffix A. I write this A because I am defining this map for A. So it is TA is from G to G and it is defined like this: TA at X is equal to AX. Now see, A is from where? A is from G. A is from G. X is also from G. G is a group. So if you consider the product of A and X, here dot is what? It is a binary operation whatever on G. So AX will be again element of G, but AX is what? It is TA at X, right? So TAX will be the element of G. So for every X in G, TAX will be the element of G. So now my map is well defined, right? Okay, now my claim is what? What is my claim? This TA is 1 1 and on 2. ये जो मेरा मैप है वो 1 1 on 2 है. So let us prove it. So let X and Y belongs to G such that TA at X is equal to TA at Y. So it gives me AX is equal to AY, and we are in group. So A belongs to G, so A inverse XG, so you just multiply both sides by A inverse on left. So it is what? X is equal to Y. So therefore TA is 1 1. Right? Now onto. So for onto what we do? You take any element from Y. Let Y belongs to G. Now I want to find one element in G, so that if I apply TA on that Y, then it is what? It becomes, it gives me Y back. So it is simple. See what I want? I want TAX should be Y, so it should be AX should be Y, right? So X should be what? It should be A inverse Y. So if I consider A inverse Y, then it will work. X is A inverse Y. So Y is in G, so implies A inverse into Y. A inverse into Y, it will be also in G. Why? Because A belongs to G. Where is A? Yes, A belongs to G. Y belongs to G. G is a group, so A inverse is in G. Y is in G, so A inverse into Y is also in G, and let me say it is X, right? So then this TAX will be what? It is AX, but AX is what? A into A inverse Y, and that is what? It is Y. So therefore TA is 1 2. TA is on 2. So TA is what? It is 1 1 on 2 map, right? So let me consider a group. Okay, let me write here. So now you consider G bar is equal to TA, where A belongs to G. So corresponding to every A in G, you consider TA. So TA is what? TA is a mapping from G to G, defined like this. So G bar is what? It is a collection of functions from G to G, and that functions are 1 1 and on 2. So अभी जो हमने शुरू में दिखाया डिस्कस किया कि सपोज X is any non-empty set and you consider AX, where AX is what? It is a F, collection of function F, where F is what? It is a mapping from X to X and it is 1 1 on 2. Then this set forms a group with respect to composition of function. So AX with composition of function forms a group. So here G bar is also what? It is also collection of functions from G to G, and they are 1 1 and on 2. So consider this, then this G bar is what? G bar with composition of function is a group, and here elements of G bar are what? 1 1 on 2 functions, so they are permutations. So then is a group, and G bar is a group of permutation. is a group of permutation on G. So now my next claim will be what? Now I will show that my this group G will be isomorphic to G bar, right? So let me remove this portion. I keep the definition of TA just for reference. Okay, so now you define phi is a mapping from G to G bar. Phi is a mapping from G to G bar. In this way, phi of A, you take any element from G, then it is what? TA for all A belongs to G. So now my claim is what? Claim is phi is an isomorphism. ये जो मेरा phi है वो isomorphism होगा. So let us prove how it is isomorphism. So for that what I need to prove, I have to show that phi is 1 onto and preserves composition. So let me remove this also. So first is phi is 1. Let A and B belongs to G such that phi A is equal to phi B. So it means what? It is TA is equal to TB. Now TA and TB are mappings from G to G. Now two maps are same. Two maps are equal. It means what? They have the same value at every point of the domain. So it gives me what? TA at X is equal to TB at X for all X belongs to G. So it means, what is the definition of TA? It is just A into X. So it is AX is equal to BX for all X belongs to G. So it gives me A equal to B, because X is in G and G is a group. So you can operate X inverse on both the side from right side. So A equal to B. So it means what? Phi A is equal to phi B. Phi A equal to phi B implies A equal to B. So therefore phi is 1. Now I want to prove phi is onto. It is clear. Phi is onto. It is clear by definition. You take any element from G bar. Let any element from G bar, then element of G bar is of the form TA, where A belongs to G. So let TA belongs to G bar. Implies A will be in G. So implies phi A will be what? By definition phi A is TA. So therefore phi is onto. Now preserves composition. So how we saw it is, now phi preserves composition. So it is also simple. You take, let any AB in G, then you look at phi AB. But what is phi AB? Phi AB will be TAB. But TAB is what? I claim that TAB is TAOB. So let us prove how it is TAOB. So let me remove this. Now what is TA? TAB. TAB will be a mapping from G to G, and it is defined as TAB at X is equal to AB at ABX. We can define in this way, right, by definition. So now A, B and X are elements of G, and we are in and G is a group, so we have associativity, so it is BX. So this is what? It is T BX. BX is again element of G, so I can say it is TA BX. TABX is what? It is A times BX, and we have it here A times BX. But this is what? TA. BX is what? It can be written as BX. So this is what? TA composition TB at X. So what I have, TAB at X is equal to TA or TBX. So TAB is what? TA or TB. But what is TAB? So therefore this is phi AB is equal to this TAB, but TAB is what? TA or TB. But TA is what? It is phi A. TB is what? It is phi B, and O is composition of the function. So therefore it is phi AB is equal to phi A phi B. तो ये phi कहाँ से कहाँ डिफाइन किया था? Phi is a mapping from G to G bar, and what I have proved, phi is 1 1 on 2 and phi AB. So between A and B there is operation of G, and it is equal to phi A and phi B, and operation between phi A and phi B is the composition of function, and here on G bar we have the operation is composition of function, right? So it means what? Phi preserves the composition, therefore phi preserves the composition. So phi from G to, so therefore phi from G to G bar is an isomorphism. So therefore G is isomorphic to G bar. तो ये क्या प्रूव हुआ? G is any group and it is isomorphic to G bar, and G bar is what? It is a group of permutation. वो हमने कंस्ट्रक्ट किया था, G दिया था, उसके हिसाब से हमने G bar डिटरमाइन किया, और हमने एक G bar कंस्ट्रक्ट किया. कैसे G bar कंस्ट्रक्ट किया था? वेयर G bar is what? It is TA where A belongs to G. G में जितने एलिमेंट है, corresponding to every element of G you consider TA. And what is TA? TA is what? It is a mapping from G to G defined as TA at X is equal to AX. So G bar is what? It is a set of function, and these functions are 1 1 and on 2, so they are permutations. So G bar is a group of permutation, and G is a any group, and it is isomorphic to G bar, and G bar is a group of permutation. So every group is isomorphic to group of permutation. So this is what Calais theorem. So this result is believed to be a very important result in group theory. Why? Because you consider any group, finite, infinite, abelian, non-abelian, doesn't matter, cyclic, non-cyclic, कोई भी group हो, then it will be isomorphic to group of permutation. मतलब किसी भी group का आपको study करना है, then you just study a group of permutation. ये कोई भी group वो कोई ना कोई group of permutation के equal है in some sense, right? So that's why we study the group of permutation, and especially Sn, right? So this is what Calais theorem. Okay, so now yes, ये मैंने ग्रुप दिया था जो G, उसके हिसाब से हमने ये G bar डिज़ाइन किया, and the recipe of G is this one. मतलब आपको कोई भी ग्रुप दिया है तो वो ग्रुप के हिसाब से आप यू कैन ऑलवेज कंस्ट्रक्ट अ ग्रुप ऑफ परम्यूटेशन सो दैट दैट ग्रुप इज आइसोमॉर्फिक टू दिस ग्रुप. तो हमारा Zn है, Un है, GLnr, SLnr, Dn, Sn. So every group will be what? It will be isomorphic to some group of permutation. Sn अपने आप में ग्रुप ऑफ परम्यूटेशन है. ओके, सो नाउ नेक्स्ट, so now let us see some variant of homomorphisms. It is just definitions, but let us list. See, we know what is homomorphism. Homomorphism is a mapping from G to G bar, and which preserves the composition phi AB equal to phi A phi B, right? So now some definitions. First one, a 1-1 homomorphism is called a monomorphism. It is just terminology कि कोई मेरा होमोमॉर्फिज्म है देन इट प्रिजर्व्स द कंपोजिशन. वो जरूरी नहीं है कि वो 1-1 है, लेकिन यदि वो 1-1 भी है देन आई विल से इट इज कॉल्ड मोनोमॉर्फिज्म, और यू मे से 1-1 homomorphism is called monomorphism. It is just definition. We just keep this in mind. If somewhere we got this word monomorphism, then it is nothing but it is 1-1 homomorphism. So if I write roughly, then it is homomorphism plus 1-1. Homomorphism plus 1-1 is equal to monomorphism. Right? Second term, an onto homomorphism is called endomorphism. Sorry, epimorphism, not endo, epimorphism. Endomorphism we will define right just now. It is called epimorphism. So homomorphism plus onto is equal to epimorphism. Again, it is just a variant of homomorphism. Now third one, 1-1 plus onto plus homo, that is isomorphism, and we have already defined it and we discussed it also, so I am not writing that definition. So 1-1 plus onto plus homo means isomorphism. Now suppose I have homomorphism, say F is a mapping from G to G bar is a homomorphism, right? Here G and G bar may be different group with different binary operation, and it may happen that G and G bar are same. That is, suppose F is a mapping from G to G is a homomorphism. Domain and codomain both are same. So in that case I will say that this homomorphism is called endomorphism. This homomorphism is called endomorphism. So what is endomorphism? A homomorphism from group to itself. A homomorphism from a group G to itself is called an endomorphism. Is called an endomorphism. So it is just a terminology, simply a special type of homomorphism, and a homomorphism is from where to where, group to itself, and we will see lots of example of endomorphism, that how many homomorphism exist from Z10 to Z10, how many homomorphism exist from Z12 to Z12 in general, Zn to Zn, how many homomorphism exist from Sn to Sn, etc. So all they are endomorphism, but we will refer them as a homomorphism, but this is just for information. That type of homomorphism is also known as endomorphism. Now fourth one, an isomorphism from a group G to itself is called an automorphism. Is called an automorphism. कोई ऐसा मेरा आइसोमॉर्फिज्म है, F suppose F is a mapping from G to G, G to G bar, and F is isomorphism. Now suppose G bar is same as G and it is isomorphism, then I will say G is automorphism, right? So we have 4 terms: monomorphism, epimorphism, endomorphism and automorphism. So all are just variant of homomorphism. One homomorphism is called monomorphism, on to homomorphism is called epimorphism. If your homomorphism has domain and codomain are equal, then it is called endomorphism, and if your isomorphism has domain and codomain are same, then it is called automorphism. So this is just for your information. So let us give one important example class of automorphism. So now example, let G be a group. Let G be a group. For A belongs to G, you fix A. You fix A belongs to G and you define phi A is a mapping from G to G, defined as phi A at X is equal to AX A inverse for all X belongs to G. मतलब ग्रुप है आपके पास, ग्रुप में इट मे बी फाइनाइट, इनफाइनाइट, साइक्लिक, नॉन साइक्लिक, अबेलियन, नॉन अबेलियन, डजंट मैटर, right? You consider a group. Now fix one element from G, and with the help of that element you consider a function phi A from G to G, and its definition is like this: if you operate phi A on the element of X, then it is A X and A inverse. मतलब ये जो एलिमेंट फिक्स किया है उस वो एलिमेंट और उसके इन्वर्स के बीच में X ले लो और इनका कंपोजिशन कंसिडर करो. Then X is in G, A is in G, so A inverse will be also in G because G is a group. So X, A and A inverse, all these 3 elements are in G, so its product will be again in G, and that is what it is, phi AX by definition. So for every X in G, phi AX is element of G, so this mapping makes sense, right? So now my claim is what? So this is set up. So then this phi A is an isomorphism. तो ये मेरा क्या होगा? It will be isomorphism, and this is an isomorphism from a group to itself, so it is called automorphism. Is an isomorphism, or you may say phi A is an automorphism. So let us give the solution. So first of all, phi A is 1 1. Let X Y belongs to G such that phi A X is equal to phi A Y. So it gives me AX A inverse is equal to AY A inverse, and we are working in group, so you can cancel A from left side and A inverse from right side, so we have X is equal to Y. You just operate A inverse on left and A on right, and you just use the associativity, you will get X equal to Y. So therefore phi A is 1 1. Now phi A is 1 2. So you take any element from let Y belongs to G from here, right, from codomain. Then you consider A inverse Y and A, then this will be the element of again G, because A is in G, A is in G, Y is in G, so A inverse Y A will be in G, and let me say it is X, so X in G. So then what I have, then what is phi A at x? So it will be AX A inverse, but x is what? A inverse y A and A inverse, and use the associativity. So A inverse is identity, A inverse identity, identity y identity, it is just y. So therefore phi A is onto. Now phi preserves composition. Phi preserves composition. So let x y belongs to G, and you look at phi A at x y. So it is what? A x x y A inverse, but it is what? A x, and here I can write A inverse into A y A inverse. A inverse A is identity, so it is simply xy, and we are in group, so we have associativity. So AX A inverse, and you keep this AY A inverse, right? So this is what? It is phi A at x, and this is AY A inverse is phi A at y. So phi A at xy is equal to phi AX phi AY, right? So phi A preserves the composition, and hence phi A is an automorphism. Phi A is an automorphism. See, तो हमारे पास यहाँ पर क्या हुआ कि कोई एक ग्रुप लिया हमने, उसमें से एक एलिमेंट फिक्स किया, देन दैट एलिमेंट गिव्स मी ऑटोमॉर्फिज्म, और दैट एलिमेंट गिव्स मी आइसोमॉर्फिज्म फ्रॉम दैट ग्रुप टू इटसेल्फ. तो मतलब ग्रुप में जितना भी एलिमेंट है, you consider A, then you have phi A. For A belongs to G, you have phi A, one automorphism. You consider B belongs to G and assume that A is not equal to B, then you have phi B, another automorphism. Now question is what? Whether they are equal or not. It may be equal, it may be distinct, it depends on the group. We'll see what happened with phi and phi B, right? So now if C belongs to G, then you consider phi C. So if this phi A, phi B, phi C all are suppose distinct, अलग अलग है, these are functions, and if they have different value at least one point, कोई एक पॉइंट पे ये डिफर कर गई ये दोनों, तो ये डिफरेंट हो गए. कोई एक पॉइंट पे ये दोनों डिफर कर गए, देन दिस टू विल बी डिफरेंट. कोई एक पॉइंट पे फाई एंड फाई सी डिफर कर गए, देन इट विल बी डिफरेंट. तो मान लो कि ये डिफरेंट मिल रहे हैं, देन फॉर एवरी एलिमेंट इन जी यू हैव डिस्टिंक्ट ऑटोमॉर्फिज्म, राइट? और ये सेम भी हो सकते हैं. ओके, लेट अस सी. Okay, first of all let me define collection of all automorphisms like this. और इस तरह से मतलब ये G2G हमने ऐसे डिफाइन किया, AX A इनवर्स. सो इसके अलावा भी मेरे पास ऑटोमॉर्फिज्म हो सकते हैं. I can define another way also, and it is isomorphism from G2G, or it is a automorphism. But इस तरह से जो मैंने डिफाइन किया उसको मैं बोलूँगा इनर ऑटोमॉर्फिज्म. दैट इज I give a special name, it is inner automorphism. So let me define. So now this is my definition. Let G be a group, then the set of inner automorphism is denoted by INN in G, and this in G is what? It is a set of all inner automorphism. Let G be a group. Okay, let me write in this way. Let G be a group then for A belongs to G, the mapping phi A is a mapping from G to G defined as phi A at x is equal to AXA inverse for all x belongs to G is called an inner automorphism. Is called an inner automorphism. And in this example we already proved that this mapping is what? It is an automorphism, or it is an isomorphism from G to G itself, so it is called automorphism. But I give the special name to this automorphism is inner automorphism. So this is my definition of inner automorphism. Moreover, the set of all inner automorphism of the group G is denoted by InnG, ING, inner set of all inner automorphism. So that is, what is my InnG? InnG is phi A where A belongs to G, where phi A is a mapping from G to G and phi A at x is equal to AXA inverse for all x in G. So this is my InnG. So this is a collection of automorphism, but special type of automorphism, and these are what वो इसी तरह से डिफाइन किए हुए ऑटोमॉर्फिज्म. इसके सिवा भी ऑटोमॉर्फिज्म हो सकते हैं, बट इट इज डिफाइंड इन दिस वे. Yes, so this is what set of all inner automorphism on G. Okay, so now let us consider one special case when what happened when G is abelian, and then let us see what is inner automorphism of G. तो क्या होगा? सही, it's let G be abelian. Finite, infinite doesn't matter, G is abelian. Let A belongs to G, and you consider phi, this is my G, okay, phi A at x, phi A is a mapping from where to where? It is from G to G. And what is the definition of phi AX? It is AXA inverse for all x belongs to G. But my G is abelian, so AX is same as XA. So this is what? AA inverse is identity, so it is simply X. So what I get? Phi A at X is what? Phi AX is just X. तो आप कोई भी phi A बनाएंगे, then you will get this map. Phi AX is X. See, for example, suppose you consider Z6, your G is Z6, it is abelian. Now you consider phi Z6 is what? 0, 1, 2, 3, 4, 5. So if you consider phi 0, then phi 0 is what? And this X can be written as what? It is phi E, right? Because this X is what? It can be considered EX E inverse. So it is what? Phi E at X, right? So it is what? Phi E at X. So phi A is what? It is phi E, right? So phi 0, then you have phi 1, then phi 2, phi 3, phi 4, phi 5. So this is what? So inner automorphism of Z6 will be what? Corresponding to every element you look at phi 0, phi 1, phi 2, phi 3, phi 4, phi 5. But according to this discussion, if my G is abelian, then phi A will be reduced to phi E. So this phi 0, 0 is here, 0 is identity na. So phi 0, phi 1 will be also phi 0, phi 2 is also phi 0, phi 0, phi 0, phi 0, 1 2 3 4 1 2 3 4 5 6 1 2 3 4 5 6. Yes, so it is simple phi 0. Repetition is not allowed in the set, so it is simply phi 0. So in Z6 is what? Phi 0. So if my G is abelian, then InnG will be what? InnG will be the singleton, and it contains only identity map, that at every element the value is same. So it is identity map. So it is a group, right, containing only one element. So InnG will reduce to only one element. ओके, अभी हमने ये प्रूव नहीं किया कि ये ग्रुप है. इनफैक्ट इट इज़ अ ग्रुप, विल सो इट इज़ अ ग्रुप. बट जब मेरा ये, सो दिस इज़ वन ऑब्जर्वेशन. सो लेट मी राइट this observation in this way. Not if G is abelian, then this InnG is what? It is singleton, this phi E only it contains only one element. InnG is, or you say what, InnG is singleton. This is very important observation. And converse is also true. If your InnG is singleton, then your G is abelian. See, InnG is singleton, then it is also abelian, but we will prove later on, or let us prove it. That is result. Let G be a group. Now InnG, G be a group. G is abelian if and only if InnG is what? This singleton phi E. तो ये तो हमने प्रूव कर दिया कि if G is abelian, then InnG is singleton phi E. Now let us prove it converse. You assume that InnG is, it contains this one, singleton phi. Now my claim is what? G is abelian. So you take, let X and Y belongs to G. You consider X and Y from G. Okay, so here we want to prove G is abelian. Okay, अभी हम ये इसको प्रूव नहीं कर रहे हैं. We will prove later on, because we have this result G quotient center of G is isomorphic to InnG. इस रिजल्ट के हेल्प से it will be easy to prove. So you forget about this, but this result is true. You just write down this result, but we will prove later on by proving this result. अभी ये हमें बाकी है प्रूव करना. So ऐसे भी प्रूव कर सकते हैं, but for that we need some little bit construction, but that one is very simple. So you just keep in mind G is abelian if and only if InnG is singleton phi E. Okay, so तो अभी हमने क्या डिस्कस किया? So let us just quickly summarize. कि यदि मेरे पास कोई फंक्शन है phi is a mapping from G to G and it is isomorphism, then it is called automorphism. Suppose phi from G to G is isomorphism, then phi is called ऑटोमॉर्फिज्म. और ये जो ऑटोमॉर्फिज्म है, ऐसे तो बहुत सारे ऑटोमॉर्फिज्म, उसमें से स्पेशल टाइप का ऑटोमॉर्फिज्म, एंड दैट इज डिफाइंड एज phi a at x is equal to for every a in G you define phi a from G to G as phi a at x is equal to ax a inverse. This is also automorphism and it is called inner automorphism. Then we collect all inner automorphism, and that set is denoted by InnG, set of all inner automorphism on G. Okay, now let us collect all automorphism. तो ये जो इनर ऑटोमॉर्फिज्म है वो भी ऑटोमॉर्फिज्म है, तो वो ऑटोमॉर्फिज्म का जो हम सेट कलेक्ट करेंगे, सेट ऑफ ऑल ऑटोमॉर्फिज्म ऑन जी, तो ये सब उसमें आ जाएंगे. सो फर्स्ट ऑफ ऑल लेट अस डिफाइन, लेट जी बी अ ग्रुप, let G be a group, then AutG is stand for AutG is equal to set of all automorphism on G. That is, if I write, then it is a collection of function f such that f is a mapping from G to G is an automorphism. This is an automorphism. So this is my AutG. So now what is my claim? So this is my result. Let, or simply AutG with the composition of function. AutG में क्या रहेंगे? Functions. कैसे functions? G to G and they are automorphism, so they are isomorphism. So AutG with composition of function is a group. ये हमारा एक ग्रुप बनेगा. So what is proof? So let us just discuss the proof. First of all, you consider any two function. First of all, I have to show that AutG is what? AutG is what? It should be non-empty. So you consider a function, say I is a mapping from G to G, defined as Ix is equal to x for all x belongs to G. So it is 1 1 on 2 and Ixy is equal to Ixy क्या रहेगा? xy, and x is Ix and y is Iy. So preserves composition. 1 1 on 2 preserves composition. So it is isomorphism from G to G, and domain codomain are same. So it is automorphism. So I belongs to AutG, and as a result AutG is non-empty, right? तो ये non-empty हो गया. Now you take any two elements from, now you take any two elements f and g from AutG. So it means what? F is a mapping from G to G, and it is automorphism. G is a mapping from G to G, and it is also automorphism. Automorphism means G to G is an isomorphism. G is also isomorphism, and we know that composition GOF, here both the function has same domain, same codomain. So f को G, GOF, whatever you want, it will be defined, right? And GOF is a mapping from G to G, and composition of two isomorphism is again isomorphism. We have already discussed. So GOF is isomorphism, and it is from G to G. So GOF is also automorphism. So if you have f and g belongs to AutG, then GOF is also automorphism. As a result, GOF belongs to AutG. Now, so first property is satisfied, closure property. Now second one, associativity. Now you take any three element f, g and h from AutG, then all this f, g and h all are mapping from G to G, and once so therefore FOGOH and FOGOH are defined, and they are also from G to G, and whenever the composition of function is defined, then it is associative. So ये equal read रहेगा. So it is this required just set theory, right, or just property of function. So second property also solved, associativity. Now what about the identity element? You consider this map I is a mapping from G to G, defined as I at x is equal to x for all x belongs to G. Then I belongs to AutG, as we had discussed. It is 1 1 on 2 preserves composition, and if you consider composition of f with I, then it will be F is equal to IOF for all F belongs to AutG. So the identity map is identity element of AutG. Now what about inverse? So if F belongs to AutG, then F is a mapping from G to G. It is a automorphism. It is automorphism. So it is therefore F from G to G is isomorphism, and we know that if phi from G to G bar is isomorphism, then phi inverse from G bar to G is also isomorphism. So here F inverse from G to G is also isomorphism. So F inverse from G to G is automorphism, and as a result F inverse belongs to AutG, and this F inverse, if you consider F inverse OF or F inverse OF, then you will get the identity map. So inverse is also there. So in short, automorphism of G with the composition of function forms a group, right? See, here I am not writing the proof in detail or systematic manner, because it is just simple based on the result and what we know, what we have information, simple information about the functions and previous some results. So I am not writing it, but at least you write in the systematic way just for your record. So automorphism of G, that is AutG, you collect all the automorphism from G to G, then it will forms the group with respect to the composition of function. Now this is first result. Second one, ये जो हमारा इनर ऑटोमॉर्फिज्म था InnG, तो इसमें क्या आ रहे थे, इसमें भी ऑटोमॉर्फिज्म थे, लेकिन सब ऑटोमॉर्फिज्म नहीं थे. इसमें कैसे ऑटोमॉर्फिज्म्स थे, स्पेशल टाइप के phi A, and we know what is the definition of phi A, right? So every element of InnG is an automorphism on G, right? And in AutG all automorphisms are there. So InnG is a subset of AutG. InnG is a subset of AutG. First observation. Third one, InnG is a subgroup of AutG. ये इसका सबग्रुप बनेगा. कैसे? Let us prove it quickly. So first of all, InnG is non-empty. How it is non-empty? First of all, it is a subset of AutG, that is fine. And InnG is a non-empty because you consider phi E. So phi E belongs to InnG. So InnG is what? It is non-empty. Now you take any two element from InnG. So let phi A and phi B belongs to InnG. ओके, तो पहले तो मुझे ये बताना पड़ेगा कि InnG अपने आप में ग्रुप है. InnG इज ऑल्सो ग्रुप विथ रिस्पेक्ट टू. ओके, लेट अस प्रूव इन दिस वे. तो ये भी पता चल जाएगा कि इसका इन्वर्स कैसा है. ओके, लेट मी, दिस इज करेक्ट, बट without using 2 step or 1 step, let us prove independently. So how it is, how we prove it? So first of all, InnG is what? It is non-empty, first thing. Now second, non-empty because this phi E belongs to InnG. Okay, now you take two elements from InnG. Let phi A and phi B belongs to InnG. So what will be phi A or phi B? So phi A or phi B is what? Phi A is a mapping from G to G, phi B is a mapping from G to G. So phi A or phi B is also a mapping from G to G. And phi A or phi B at X, it will be what? It will be phi A at phi B at X. So this will be what? It will be phi A Bx B inverse. So this will be what? It is A Bx B inverse A inverse, and that is what? It is AB X B inverse A inverse. So I can write it is AB inverse. So it will be B inverse A inverse, right? So this is what? It is phi AB at X, right? तो ये क्या प्रूव हुआ? Phi A or phi B is equal to phi AB, and this is true for every X in G. So phi A or B is phi AB. So it is what? It is an element of InnG, because इसका जो form है phi suffix AB. So if you take any two elements from InnG, then its composition is also InnG. Okay, now composition. So clearly phi A or phi B or phi C will be same as phi A or phi B or phi C, because composition of function is always associative whenever it is defined. And here phi A, phi B, phi C are mapping from G to G. So this composition and these compositions are defined, and once it is defined, it is associative. So no need to prove that in detail. Now, so second property is clear. Now third one, it is a existence of identity. So clearly this phi E belongs to InnG. जब हमने वो नॉन एम्प्टी दिखाया था तब, right? So then what will be phi A? Then for any phi A belongs to InnG, you look at phi A or phi E. So it will be what? See, यहाँ से हमें एक डेफिनेशन मिल रही है कि ये दोनों दो इनर ऑटोमॉर्फिज्म लेंगे तो उसका कंपोजिशन कैसे फाइंड करेंगे, जो सफिक्स में उन दोनों का प्रोडक्ट कर दो. So here AE, so you just find just consider phi A dot E, and that is phi AE is what? It is A. So phi A or E is phi A, and similarly phi E or phi A will be phi EA, and that is what? Phi A. So therefore phi E belongs to InnG is the identity. It is the identity element. Now inverse. इन्वर्स कैसे निकालेंगे? See, you take phi A belongs to InnG. तो इसका मतलब क्या हुआ? A belongs to G. ये A कहाँ पे रहेगा? G में. So A inverse will be also in G. So you consider phi A inverse, so it will be element of InnG, right? Now you consider this phi A or phi A inverse. तो ये क्या रहेगा? phi A or phi B, so it is A into B. So A into A inverse, and that is what? Phi E. And similarly you can have phi A inverse or phi A inverse or phi A. It is what? Phi A inverse A, and that is phi E. So phi A or phi A inverse is equal to phi E equal to phi A inverse or phi A. So product of these two, composition of two functions is identity map in either way. So phi A inverse is what? Phi A inverse. So here we got a rule how to find the inverse of inner automorphism. So phi A inverse is just you apply the inverse on the element, so you will get inverse of inner automorphism, and phi A inverse is an element of inner automorphism of G. So every element of inner automorphism G has inverse in inner automorphism of G. So inner automorphism of G with the composition of function forms a group, right? तो ये इसका सबसेट है और दोनों ये और ये दोनों सेम ऑपरेशन के साथ ग्रुप बना रहे हैं. सो दिस वन इज अ ग्रुप, देन दिस इज अ सब ग्रुप. सो इनर ऑटोमॉर्फिज्म G इज अ सब ग्रुप ऑफ इनर ऑटोमॉर्फिज्म ऑफ G. Now fourth one, it is a subgroup, but not only subgroup. You can show that in fact it is a normal subgroup of automorphism of G. तो पहले तो क्या हुआ, ऑटोमॉर्फिज्म का ये सबसेट था, फिर पता चला वो सब ग्रुप है. नाउ वी क्लेम दैट इट इज अ नॉर्मल सब ग्रुप. तो सब ग्रुप है वो तो पता ही है, अब मुझे सिर्फ दिखाना है इट इज अ नॉर्मल सब ग्रुप. सो यू टेक वन एलिमेंट फ्रॉम हियर, वन एलिमेंट फ्रॉम हियर, एंड यू जस्ट कंसिडर दैट कंपोजिशन, and you saw that composition is in G. So let us complete this one also. So let one element say F from automorphism of G, and one element say phi A from InnG. Now I want to show that this one is a normal in this one. So you look at this composition, phi A F F inverse. So F is a mapping, so you look at this composition first of all. So see, F is a mapping from where to where? It is from G to G, and it is automorphism, so it is isomorphism. So it is 1 1 on 2 inverse exists, and its inverse is also isomorphism. So F from G to G, it is an automorphism. So F inverse from G to G exists, and it is also automorphism. So in short, F is G to G, then F inverse is also from G to G. Now phi A is also mapping from G to G. So F, F inverse and phi A all are from G to G. So F phi A F inverse will be a mapping from G to G. ये G to G का मैप रहेगा, right? But my claim is what? So claim is this one. This F phi A F inverse is an element of inner automorphism G. This is my claim. So to prove this claim, what I have to show? I have to show that F phi A F inverse, it is of the from phi and something here, and this something it should be element of G. ऐसा कुछ दिखाना पड़ेगा. I have to show this. Okay, so to show this, first of all, F phi A F inverse is a mapping from G to G. Now F phi A and F inverse all are automorphism, so its composition is also automorphism. Actually it is composition O, right? But I am not writing here, it is O. So let me write here F O phi A O F inverse. तो ये पहले ऑटोमॉर्फिज्म तो है, लेकिन बट आई वांट टू शो दैट ऑटोमॉर्फिज्म इज ऑफ द फॉर्म phi suffix some element of G. So how we prove it? See, F of phi A F inverse, let me evaluate it at X, and where X is any element of G. So it is what? F O phi A at F inverse X. And what is the definition of this one? It is F at phi A at F inverse X. Correct? And what is the definition of this phi A? It is F at phi A F inverse X. Okay, it is phi F of phi A F inverse X. Okay, so now yes, so see phi a at f inverse x. First f inverse applied on x, then phi a. Okay, so see this. Okay, let me recall. Phi a is a mapping from G to G, and phi a at x is what it is. Ax, a inverse definition of phi a is like this, right? So now phi a is applied here, so it is what f at a f inverse x, a inverse, right? Here x is what f inverse x, so it will be applied here like this. So phi a at f inverse x is what a f inverse x, a inverse. Now what is my f? F is automorphism, so f is automorphism, so it will preserve composition. Now a is in G, see, a is in G. Now x is where? Here x is in G, so f inverse x, f is a mapping from G to G, x belongs to G, so f inverse x will be also in G. Here x in G, so f inverse x will be also in G. So here a, f inverse x and a inverse all are elements of G, and f is a automorphism from G to G, so it is isomorphism, so it will preserve composition. So it is fa, f of f inverse x, and it is fa inverse, fa inverse. So this is what it is, fa, f of f inverse is identity, so it is x, and it is f a inverse, but f a inverse because f is isomorphism, so you can take minus sign outside the bracket. So this is what I can write, it is phi of f of a at x, fa x, fa inverse. So this is true for every x in G. So what I have proved, f of phi a of f inverse, it is phi of fa. Now a belongs to G, so a belongs to G, so fa will be also in G because f is a mapping from G to G. So f of phi a f inverse is phi f of a, and now this is an element of inner automorphism of G. तो ये हमारा क्लेम था, f I a f inverse is in G, it is true. So it is a normal subgroup. Okay. So see, whenever we have normal subgroup, suppose H is a normal subgroup of G, then we always talk about G quotient H. So this is a group, it is a normal subgroup of AutG. Then we have this natural question, what is AutG quotient in G? And this type of questions are many times asked in various exams like GAT, NBHM, NET, GSET, right? So we'll deal with this. So what is AutG quotient in G? And G is suppose SN, G is suppose SN or DN, GLNR, SLNR, right? तो ये क्या रहेगा? So for that we need something more, then we'll discuss this type of problems. ओके तो अभी हमारे पास क्या इन्फॉर्मेशन है कि इस लेक्चर में हमने क्या डिस्कस किया स्टार्टिंग से, होमोमॉर्फिज्म एंड आइसोमॉर्फिज्म के कुछ वेरिएंट्स डिफाइन किए, मोनोमॉर्फिज्म, एपीमॉर्फिज्म, एंडोमॉर्फिज्म, ऑटोमॉर्फिज्म. फिर कोई भी ग्रुप है देन यू कलेक्ट ऑल ऑटोमॉर्फिज्म्स ऑन जी, देन देयर इज वन सेट दैट इज AutG. and AutG with composition of function forms a group. That is one thing. Then you consider spatial type of automorphism, and it is called inner automorphism, and you collect all inner automorphisms. Then we have another set InnG, and it is with composition of function forms a group. And we have inner automorphism is a subset of automorphism. Not only subset, it is a subgroup. Not only subgroup, it is a normal subgroup. So inner automorphism is a normal subgroup of automorphism of G. So that is one line conclusion of up to this discussion. और बीच में एक रिजल्ट हमने देखा था, अभी प्रूव नहीं किया, वो वन वे इज प्रूव्ड बट अनदर वे इज नॉट प्रूव्ड. Intentionally I am not proving it because I want to prove it with the help of some other result, and that is what inner automorphism. Okay, तो हमने ये जो रिजल्ट प्रूव किया था, G is abelian. G is abelian implies InnG is what? InnG is singleton phi e. तो वो सिंगलटन मिल रहा है, मतलब ये अपने आप में ग्रुप है, वो तो हमने प्रूव कर दिया. तो जब G अबेलियन है तो वो अबेलियन ग्रुप को लेके आप जब इनर ऑटोमॉर्फिज्म ऑफ G बनाएंगे तो उसमें एक ही एलिमेंट रहेगा, वन एलिमेंट, ऐसा ग्रुप के जिसमें एक ही एलिमेंट है, देन दैट इज व्हाट, इट इज सिंगलटन E, means it is Z1, right? And it is, so it is a cyclic group. So whenever G is abelian, InnG is always cyclic. So that is one line. Whenever G is abelian, InnG is cyclic. In fact, it is a trivial group, right? InnG is trivial. So this is what up to here. So we stop this lecture here, and in the next lecture we'll continue with homomorphism and isomorphism, some further discussion on homomorphism and isomorphism, and we have lots of work on homomorphism and isomorphism. So we stop this lecture here. Thank you.